6th International Physics Olympiad, year 1972, IPHO, problem number 1. 3 cylinders with the same mass, the same length, and the same external radius are initially resting on an inclined plane. The coefficient of sliding friction on the inclined plane, mu, is known and has the same value for all the cylinders. The first cylinder is empty tube. The second is a homogeneous field, and the third has a cavity exactly like the first, but closed with 2 negligible mass leads and filled with liquid with the same density like the cylinder's walls. The friction between the liquid and the cylinder wall is considered negligible. The density of the material of the first cylinder is n times greater than that of the second or of the third cylinder. Determine A. The linear acceleration of the cylinders in the non-sliding case. Compare all the accelerations. B. Condition for angle alpha of the inclined plane so that no cylinders is sliding. C. Reciprocal ratios of the angular accelerations in the case of rollover with the sliding of all the 3 cylinders. Make a comparison between these accelerations. D. The interaction force between the liquid and the walls of the cylinder in the case of sliding of this cylinder, known that the liquid mass is ml. Solution for problem number 1. The inertia moments of the 3 cylinders are I1, where we have internal radius small r and the external radius is big R. This one. For second one we have totally external radius r, and for the third cylinder we have internal radius is the same as for the first one, external is for the same one, and also it's filled with the same density inside the cylinder of liquid. Because the 3 cylinders have the same mass, we have mass equal rho 1 multiplied by pi multiplied by r square minus r small square, which is equal to rho 2 pi r square h. And also we have that rho 1 equal n times rho 2. So from this data we can find that small r square equal big R square multiplied by 1 minus 1 over n. Now moment of inertia of all 3 cylinders could be written in form of I1 equal I2 multiplied by 2 minus 1 over n, and I3 equal I1 over n. It means that for n greater than 1 we have I1 greater than I2, which is greater than I3. For a cylinder rolling over freely on the inclined plane, we can write the equations. Ma equal mg sine alpha minus force of friction, I beta equal F force of friction multiplied by external radius, and the normal force equal mg cosine alpha, where beta is the angular acceleration. If the cylinder doesn't slide, we have the condition that acceleration A equal beta r. Solving the equation system from 6 to 8, we can find that acceleration A equal g sine alpha over 1 plus I over mr square, and the force of friction equal mg sine alpha over 1 plus mr square over I. The condition of non-sliding is next one. Force of friction must be less than mu n, which is equal mu mg cosine alpha. It means that tangent alpha must be less than mu multiplied by 1 plus mr square over I1. In the case of the cylinders from this problem, the condition necessary to show that none of them slides is obtained for maximum I. So we have I1 equal I2 multiplied by 2 minus 1 over n, which is equal mr square multiplied by 2n minus 1 over 2n. It means that tangent alpha must be less than mu multiplied by 1 plus mr square over I1, which is equal mu multiplied by 4n minus 1 over 2n minus 1. The accelerations for cylinders are a equal g sine alpha over 1 plus I over mr square, and in each case we have a1 equal 2g sine alpha over 3 plus 1 minus 1 over n, a2 equal 2g sine alpha over 3, and a3 equal 2g sine alpha over 3 minus 1 over n squared. So it means that a1 less than a2, which is less than a3. In the case then all the three cylinders slide, we have force of friction F equal mu n, which equal mu mg cosine alpha. And from equation number 7 we have angular acceleration equal r over I multiplied by 1 mg cosine alpha. And for the cylinders of the problem we have such conditions that angular accelerations back proportional to moment of inertia, which is this one. So it means that beta 1 less than beta 2, which less than beta 3. In the case that one of the cylinders is sliding, we have ma equal mg sine alpha minus force of friction, where force of friction equal mu mg cosine alpha, and the acceleration a equal g multiplied by sine alpha minus mu cosine alpha. Now let's force F be the total force acting on the liquid mass ml inside the cylinder. We can write that force F in x direction plus mlg sine alpha equal mla, which is mlg multiplied by sine alpha minus mu cosine alpha, and fy minus mlg cosine alpha equals 0. And in that case we have force F equal fx square plus fy square, which is mlg cosine alpha multiplied by square root from 1 plus mu square, which is equal to mlg cosine alpha over cosine phi, where phi is the friction angle, tangent phi equal mu. So that was a full solution for problem number 1. 6th International Physics Olympiad year 1972 IPHO, problem number 2. Two cylinders A and B with the equal diameters have inside two pistons with the negligible mass connected by a rigid rod. The pistons can move freely. The rod is a short tube with a valve. The valve is initially closed. The cylinder A and his piston is adiabatically insulated and the cylinder B is in thermal contact with the thermostat, which has the temperature theta equal 27 degrees Celsius. Initially the piston of the cylinder A is fixed, and inside there is a mass M equal 32 kg of argon at a pressure higher than the atmospheric pressure. Inside the cylinder B there is a mass of oxygen at the normal atmospheric pressure. Liberating the piston of the cylinder A, it moves slowly enough, quasi-static, and at equilibrium the volume of the gas is 8 times higher, and in the cylinder B the oxygen's density increased 2 times. Knowing that the thermostat received the heat Q prime equal 747.9 by 10 power 4 joules, determine A. Established on the base of the kinetic theory of the gases, studying the elastic collisions of the molecules with the piston, that the thermal equation of the process taking place in the cylinder A is T multiplied by V power 2/3 equal constant. Question B. Calculate the parameters P, V and T of argon in the initial and the final states. Question C. Opening the valve which separates the two cylinders, calculate the final pressure of the mixture of the gases. The kilomolar mass of argon is mu equal 40 kg per kilomole. Solution for problem number 2. Question A. We consider argon an ideal monoatomic gas and the collisions of the atoms with the piston perfect elastic. In such a collision with a fixed wall, the speed v of the particle changes only in the direction, so that the speed v and the speed v prime after collision they are in the same plane with the normal and the incident and the reflection angle are equal. So it means that the normal angle is opposite and tangential is the same one. In the problem, the wall moves with the speed u perpendicular on the wall. The relative speed of the particle with respect to wall is v minus u. Choosing the OZ axis perpendicular on the wall in the sense of u, the conditions of the elastic give such directions. We see that in xy plane we have the same velocity, but in z plane we have v prime equal to u minus vz original. So the increase of the kinetic energy of the particle with mass m0 after collision is equation number 3, which finally give us negative 2m0 u vz, because u is much smaller than vz. If nk is the number of molecules from unit volume with the speed component vzk, then the number of molecules with this component which collide in the time delta t, the area delta s of the piston is this one, 1/2 nk multiplied by vzk and multiplied by delta t and delta s. These molecules will have a change of the kinetic energy like this. Here we have delta v equal u, delta t, delta s is the increase of the volume of gas. The change of the kinetic energy of the gas corresponding to the increase of volume delta v is this one. Here we use this knowledge that in direction z the root mean square 3 times less than root mean square from all directions. And we can rewrite it like this. Now we just need to integrate this equation to get result, which is total energy multiplied by V power 2/3 is constant. The internal energy of the ideal monoatomic gas is proportional with the absolute temperature T, and the equation 8 can be rewritten like this. TV power 2/3 is constant. This was a solution for question A. Solution for question B. The oxygen is in contact with the thermostat and will suffer an isothermal process. The internal energy will be modified only by the adiabatic process suffering by argon gas. So we have delta U equal nu multiplied by CV multiplied by delta T, which is equal to mass of argon multiplied by CV multiplied by delta T, where mu is the number of kilomoles for argon. CV equal 3/2R. For the entire system, L equals 0 and delta U equal Q. We will use indices 1 respectively 2 for the measures corresponding to argon from cylinder A, respectively oxygen from the cylinder B. It means that delta U equal m1/mu1 multiplied by 3/2R and multiplied by temperature difference T1 prime minus T1, which is equal Q, and which is equal to this expression when we use previous conditions for TV. From equation 11 we have T1 equal this expression, which is 1000 Kelvin, so it means that T1 prime equal T1/4, which is 250 Kelvin. For the isothermal process suffered by oxygen, we have rho prime 2 over rho 2 equal P prime 2 over P2, where we have P prime 2 equal 2 atmospheres. And from the equilibrium condition we have P prime 1 equal P prime 2, which is 2 atmospheres. And for argon we have P1 equal P prime 1 multiplied by V prime 1 over V1 multiplied by T1 over T prime 1, which is 64 atmospheres or 64.9 multiplied by 10 power 5 Newton per square meter. And for volume V1 we have m1/mu1 multiplied by RT1 over T1, which is 1.02 cubic meters, and V prime 1 equal 8 times V1, which is 8.16 cubic meters. So that was solution for question B. Solution for question C. Opening the valve which separates the two cylinders, calculate the final pressure of the mixture of the gases. The kilomolar mass of argon is mu equal 40 kg per kilomole. When the valve is opened, the gases intermix, and at thermal equilibrium the final pressure will be P prime and the temperature T. The total number of kilomoles is constant. And we can write that nu1 plus nu2 equal nu prime P prime 1 multiplied by V prime 1 over R T prime 1 plus P prime 2 over V prime 2 P prime 2 V prime 2 over R T prime 2. It means that T prime 1 V prime 1 over R T prime 1 plus P prime 2 V prime 2 over R T prime 2 equal P multiplied by V prime 1 plus V prime 2 over RT. Here we have P prime 1 plus P prime 2 equal 2 atmospheres, and T2 equal T prime 2 equal 300 Kelvin. The total volume of the system is constant, so we have V1 plus V2 equal V prime 1 plus V prime 2, and because V prime 2 over V2 equal rho 2 over rho prime 2, we have V prime 2 equal V2 over 2 or 7.14 cubic meters. And from equation 18 results the final pressure. We have pressure equal P prime 1 multiplied by 1 over V1 plus V2 multiplied by V prime 1 by T over T prime 1 plus V prime 2, which is 2.2 atmospheres or 2.23 multiplied by 10 power 5 Newton per square meters. So that was solution for question C. 6th International Physics Olympiad, year 1972, IPHO. Problem number 3. A plane capacitor with rectangular plates is fixed in a vertical position, having the lower part in contact with the dielectric liquid. Determine the height h of the liquid between the plates and explain the phenomenon. The capillarity effects are neglected. It is supposed that the distance between the plates is much smaller than the linear dimensions of the plates. It is known the initial intensity of the electric field of the charged capacitor E, the density ρ, the relative electric permittivity epsilon r of the liquid, and the height big H of the plates of the capacitor. Solution for problem number 3. The initial energy of the capacitor is W0 equal 1/2 C0 U0 square, or 1/2 Q0 square over C0. Here we have capacitance C0 equal epsilon 0 big H L over D. H is the height of the plates, L is the width of the capacitor's plates, and D is the distance between the plates. When the plates contact the liquid's surface, on the dielectric liquid is exerted a vertical force. The total electric charge remains constant and there is no energy transferred to the system from outside. The increase of the gravitational energy is compensated by the decrease of the electric energy on the capacitor. So initially we have electric charge Q0 equal electric field multiplied by epsilon 0 and multiplied by L and big H. So we have W0 equal W1 plus W2, where W1 equal total capacitance, which is 1/2 Q0 square over C, and W2, that's potential energy, which is 1/2 rho G H square L D. Now we can count what is the total capacitance. That will be C1 plus C2, which is this expression. Now we're ready to use expression for energy conservation, because initial energy must be equal to final energy. So initial energy is W0 and the final energy is W1 plus W2. So we have expression number 5, which we got from first 4 equations. This equation Here on the left side we have change of electric energy for capacitor, and on the right side change of potential energy for the electric. Now we can use expressions for Q0, C0, C1 and C2 and get this result. From this result we can subtract many things like L, D, epsilon 0, and finally get this one. From the first look we can check that this equation of the third power, but after that we can see that we have coefficient h, it's the same on the left and on the right side. So it means that for h equals 0 we have a trivial solution, which is obvious because in initial position energy equal to final position. So we can subtract this h one time and get final result for equation. This will be equation for the second order, and for this equation we have two roots. One is positive and other is negative. You don't need negative because negative is for the electric level less than 0, and for positive we have this one. So that will be solution for this problem, but let's investigate it further, because if we check big H much greater than small h, we have for big H much greater than small h, we can express this square root through 1 plus very small number. So we have this expression, 1 and 1 cancelled, and finally we will get h approximately equal this 1. So that was a full solution for problem number 3. 6th International Physics Olympiad year 1972 IPHO. Problem number 4. A thin lens plane convex with the diameter 2 small r, the curvature radius big R, and the refractive index n0 is positioned so that on its left side is r, n1 equal 1, and on its right side there is a transparent medium with the refractive index n2 not equal to 1. The convex face of the lens is directed towards r. In the r at the distance s1 from the lens measured on the principal optic axis, there is a punctual source of monochromatic light. Question A. Demonstrate using Gauss approximation that between the position of the image given by the distance s2 from the lens and the position of the light source exists the relation f1 over s1 plus f2 over s2 equal 1, where f1 and f2 are the focal distances of the lens in r, respectively, in the medium with the refractive index n2. Observation. All the refractive indexes are absolute indexes. Question B. The lens is cut perpendicular on its plane face in two equal parts. These parts are moved away at a distance delta much less than r. Billet lens. On the symmetry axis of the system obtained is LED, a punctual source of light at the distance s1 greater than f1. On the right side of the lens there is a screen E at the distance d. The screen is parallel with the plane face of the lens. On this screen there are n interference fringes if on the right side of the lens is r. Determine n function of the wavelength. Solution for problem number 4. Part A. From the Fermat principle, it results that the time the light arrives from point P1 to point P2 is not dependent of the way. In Gauss approximation, P1 and P2 are conjugated points. Time T1 is the time the light roams the optical way. P1, V1, O, V2, P2. We have T1 equal P1M over nu1 plus P2M over nu2, where nu1 and nu2 are speed of lights in represented mediums. So we have P1M equals square root from P1O square plus MO square, which is approximately this expression, and the same thing for P2M, which is approximately this expression. This is because H equal OM is much smaller than the P1O or P1O or P2O. So we have T1 equal approximately this expression. And the T2, the way from P1 through the optical axis, that will be P1 V1 over nu1 plus P2 V2 over nu2 plus V1 V2 over nu. So from the same approximation we have V1 V2 equal H square over 2 multiplied by 1 over R1 plus 1 over R2. And because we have T1 equal T2, we can equalize them and get such result. After subtracting P1O over nu1, P2O over nu2, and get rid of H square over 2, we have this expression. Now because nu equal C over N0, nu1 equals C over N1, and nu2 equals C over N2, and also we have P1O equal S1 and P2O equal S2. Instead of equation number 3, we have equation number 4. If the point P1 is at infinite, S becomes the focal distance, and the same for P2. So we have 1 over F2 equal 1 over N2 multiplied by this expression, and the same thing for 1 over F1 equal 1 over N1 multiplied by the same expression. But these two expressions exactly equal to previous expressions in number 4. So we can combine number 4 and number 5 and find that 1 over F2 equal this one, and 1 over F1 equal this one. And the last thing is F1 over S1 equal this one, and F2 over S2 equal this one. Now we can just add them and get finally our result. F1 over S1 plus F2 over S2 equal 1. In our case, the lens is plane convex, like in this figure. It means that if we use expression from 5, we can get that for R2 equal infinity and R1 equal R, we will get these expressions, and that was a solution for the question A, problem number 4. Problem 4, question B. The lens is cut perpendicular on its plane face into equal parts. These parts are moved away at a distance delta, this one from O to O1 and from O to O2, such way that delta much less than R. Billet lens. On the symmetry axis of the system obtained is let a punctual source of light at the distance S1. S1 is greater than F1. On the right side of the lens there is a screen E at the distance D. The screen is parallel with the plane face of the lens. On this screen there are n interference fringes if on the right side of the lens is higher. Determine n function of the wavelength. Solution. In the case of a billet lens, S1 and S2 are real images of the object S, and they can be considered like the coherent light sources. Now let's count what happened. Suppose that distance from R to A equal to x. In that case we can estimate S prime A, this one S prime A, approximately equal D, this distance from lens to screen, minus P2, this one. And from this triangle SRA compared to triangle S prime Q, we have x over D minus P2 equal R over D. And finally, distance x from R to A equal D minus P2 multiplied by R over D. Now let's count what happened to distance S1Q. Suppose that S1Q, this one, equal to y. In that case, again compare triangles. We have y over P1 plus P2 equal delta, which is distance from 0 to 01 over P1. This is from these two triangles. And then from here we can find that y equal this expression, delta multiplied by 1 plus P2 over P1. And the last thing is distance QA, this one. That's equal to D minus P2. So now we have all parameters for prism S1R, R prime, S2. So that's a right prism with the known basis and no height. So from here we can find what is distance difference between S2R and S1R. Let's count it. So from the right triangle we can see that S1R square, that's equal to D minus P2 square, this one, plus X minus Y square. So this distance minus this distance. And from other hand we have S2R square, this one, that's equal the same D minus P2 square, the height, plus X plus Y square. Now we need to add X and Y. And now let's count what is the difference between these two parts. In our assumption, we can say that this distance difference equal K multiplied by lambda, where K is maximum number of these interference fringes from one side, which is equal this difference. And when we take out D minus P2, we have this expression. And in this expression, we have difference between square roots from 1 plus something small minus square root from other 1 plus something small. So we can use approximation. That will be this expression. And after calculations, we have a simple expression. 2 multiplied by xy over D minus P2. And finally we can put x and y from initial expressions from the first and the second equations, and we have k lambda equal 2 delta multiplied by small r over D and multiplied by 1 plus P2 over P1. And now we can remember what is focal distance f for our length. That will be 1 over P1 plus 1 over P2 equal 1 over F. And we can put this P2 expression to this one, and finally we will get that K equal this expression. Remember that K is just half of our wavelength, and we didn't count zero interference. So it means that the total number N will be equal to K plus 1, which is this expression. That was a solution for second question of problem number 4.